Welcome back, everyone. This is part one of my presentation, Introduction to HLSL and DXIL for beginners. First slide. What are shaders? A shader is a computer program which manipulates a 3D scene during the rendering pipeline. These manipulations are used to do graphics processing and special effects, such as color effects, shape effects, such as waves, lighting, and shading, giving pixels dark or bad shades for depiction of depth perception in 3D models by varying the level of darkness. We can program shaders to alter the position, brightness, contrast, hue, and other effects on all pixels, vertices, or textures used to produce the final image. Shader programs run on the graphics card or GPU, the graphics processing unit, instead of on the CPU, which enables us to take advantage of the parallelism inherent in GPU architectures. Shaders are executed in parallel at least once for every pixel on the screen. Note that not all shaders are executed for each pixel though. Vertex shaders, compute shaders, and other ones are exceptions to this rule. So writing shader code is in a paradigm of implicit parallelism, meaning that the shader code is programmed as serial code, but it actually executes in parallel. Each of the executions runs simultaneously on different threads in the GPU. The shader is a function which is invoked given input data identifying the pixel, which may be the XY position of the pixel on the screen or the old RGB color of the pixel. Effects such as gradients can be achieved by varying the RGB color according to the position. Now, rendering is the process of converting a 3D graphics model into a 2D image to be displayed on the screen. There are two kinds of rendering. First one, rasterization. In order for producing the 2D image, it asks the question, what pixels does geometry cover? Loops over the triangles in the scene for determining which pixels are inside which triangles. It makes use of matrix transformations from the 3D or object space into the 2D or screen space. Second one, ray tracing. In order for producing the 2D image, it asks the question, what is visible along this ray? It shoots out at least one ray per pixel in the 2D screen, meaning the viewport, not the actual monitor. The rays bounce around the 3D scene in a physics simulation, getting absorbed, reflected, and reflected. Whatever the ray touches can be seen from the screen. A structured data is passed along with the ray, which records information about intersections. This is useful for producing effects such as lighting, transparency, mirroring, shadows, and transparent shadows that may be caused, for example, by stained glass. These are all a natural side effect of the ray tracing algorithm. No special tricks are necessary. Now let's look at what is the difference between rasterization versus ray tracing. Starting with ray tracing, here is the high level, very high level shader code. It looks for each pixel or each ray. That it looks for each triangle and it asks the question, does the ray hit the triangle? And it keeps the closest hit, meaning the triangle that the ray hits first. So this is a ray-centric algorithm. And then in rasterization, it looks for each triangle, then for each pixel it asks the question, does the triangle cover the pixel? And it keeps the closest hit, meaning the triangle that is the closest to the camera. It is a triangle-centric algorithm, as you see here. So looking at these very high-level pseudocodes, the difference in the pseudocode is only the order of these two outer loops right here. And then ray tracing needs the entire scene description and memory at once, because the rays can bounce anywhere. However, the rasterizer only needs one triangle at a time, plus the entire image and associated depth information for the pixels to know which triangle is in front. So comparing that to ray tracing, which needs the entire scene in the memory, it takes up much more memory. So we can say that rasterization is a more memory efficient algorithm, but ray tracing gives us more realistic graphics effects. Now let us look at the different types of shaders that we can have. They are in two categories. We have the rasterization shaders and we have the ray tracing shaders. The vertex shader, so for the rasterization shaders we have vertex shader, pixel shader, also called fragment shader, compute shader, geometry shader, and tessellation shader. So the vertex shader is executed for each vertex that is submitted by the application. It is used to modify the position of vertex, color, and texture coordinates in the rendering process. It can make changes to vertices that already exist, but they cannot create new vertices. It is primarily responsible for transforming the vertex from object space to view space, generating texture coordinates, and calculating lighting coefficients such as the vertex tangent, binormal, and normal vectors. And it can also move the vertices around for special effects such as water rippling. These are simple vertex transformations of 3D models. Now the pixel shaders, also known as the fragment shaders, deal with effects on individual pixels. Run at least once on every single pixel, working out what color each individual pixel should be in. Pixel shaders enables a variety of visual effects, such as translucency, shadows, fogging, and lighting. And using bump maps or normal maps to affect how the geometry looks when it is reacting to light, giving the illusion of depth and texture on a flat surface for saving polygons for three-dimensional objects. And then we also have compute shaders, which is not the main focus of my presentation, but I'm going to mention it anyway. The compute shader is used to compute arbitrary information and is not directly used in drawing triangles and pixels. It has no user-defined inputs and outputs. The compute shader has to fetch the data itself. This is used for GPU, using the GPU for general purpose computing tasks. Compute shaders are individual shaders providing instructions for complete GPU tasks. In contrast with vertex and pixel shaders, which are just a subset of a more complex graphics pipeline, as we will see shortly. The compute shader by itself specifies the entire task from start to finish. It is an independent code which does not rely on the outside system as much as vertex and pixel shaders. So it is more like a C++ function Also in the rasterization shaders, we have geometry and tessellation shaders, but we're not going to talk about these today. Also, we have special shaders for ray tracing, such as ray generation shader, a mist shader, and a group of hit shaders. There are three of them. First is the closest hit shader, any hit shader, and intersection shader. So these vertex, not vector, vertex and pixel shaders are the main focus of this presentation. The ray tracing shaders, I will go over them in a future presentation. Now we're gonna look at some rendering methods for shaders. These are particularly relevant for ray tracing shaders, although these are generic methods applicable to all kinds of shaders. We have real-time shaders. Their highest priority is real-time speed. Because these shaders execute in real time, we don't want them to be lagging. Since these shaders have to be rendered at over 30 frames per second, a lot of other things have to be sacrificed in order to achieve the required speed, which is an example of time versus space trade-offs. Unlike offline shaders, real-time shaders do not use all the lights in the scene. The more lights you add to the scene, the slower it renders. Usually, they only use up to 3 lights, and each only light has to be specifically programmed into the shader. So, real-time rendering is, in the context of ray tracing, is used for video games. For example, Cyberpunk 2077 is an example of a video game which includes real-time rendering for ray tracing. So real-time rendering needs to give results when you ask for it in real time, which is how video games work. Usually the time window is around 20 milliseconds. This enables many solutions that can be used to maximize efficiency. Many tricks are used to make it seem realistic. In contrast to that, offline shaders have no time constraint. Convenience and image quality are highest priorities. They use all the lights in the scene, and it takes as long as it wants to do the math. So offline rendering is used for movies. Offline rendering has no time constraint, and more complex shading techniques can be used to get more realistic end result. Images are pre-processed or pre-calculated, and they can be assembled to like a video clip or other uses. So all the frames are stacked together into a single movie. Let's talk about computer graphics rasterization pipeline. First, a 3D graphics program sends 3D instructions to the Direct3D API. Then Direct3D takes those instructions and passes them from the GPU, from the CPU onto the GPU. So this is the CPU-GPU boundary. Above, everything is on the CPU processing, and below is everything on the GPU processing. The graphics chip receives these instructions in an area of the GPU called GPU front end, which is responsible for communicating with the CPU and receiving instructions from it. The data of the vertices is then passed into the programmable vertex processor. These vertices are transformed, the vertices in the 3D object space get transformed into the space that they will be drawn on the screen. The vertex shader written by the programmer also runs at this stage. It is able to modify the vertices, adding special effects, and it prepares the data for the pixel shaders, and then it passes the data, the transformed vertices, into the primitive assembly. Primitive assembly connects the dots between the vertices to create triangles, which are the assembled polygons, and also lines and points. And it passes them to the rasterization and interpolation unit. Rasterization and interpolation cuts up the triangles into pixels that represent that triangle. The triangles represent lines and points, and they get converted into individual pixels. Also, interpolation of the vertex data into the pixels occurs. What is interpolation? It determines the color of the pixels based on their position in the triangle. Based on their proximity to the colored vertices, they get assigned various different colors. So it is the process of transferring colors from the 3D model into assigning colors for each individual pixel. The programmable pixel processor, or also called programmable fragment processor, because fragment is another word for pixel. It contains the pixel shader, which is written by the programmer. It takes that interpolated data to determine the final color of the pixel. That data comes out of the vertex shader, and after interpolation, it comes into the pixel shader. After the pixel runs, the data is sent out to the raster operations, and then the pixels get sent to the frame buffer, where they wait to get added to the screen. So the vertex and the pixel shaders are automatically called back with the correct parameters by the DirectX API. Indeed, they are the only programmable parts of the computer graphics rasterization pipeline, and all the other parts of this pipeline are algorithms implemented in the GPU hardware. If any of you are familiar with Verilog code, you know that we can implement an algorithm in the software or the hardware. So the vertex shader runs in the programmable vertex processor, and it operates on the vertices. It takes a vertex shader input struct, and it returns a vertex shader output struct. The pixel shader runs in the programmable fragment processor, and it operates on individual pixels. Takes the vertex shader output struct as the input into the pixel shader, and returns float for color for each pixel. Both the vertex shader and the pixel shader have access to the user input data and transformation matrices, which are coming from the 3D application. More on that later. Now, there are more pixels than vertices. For example, a single triangle, you have 3 vertices versus hundreds of pixels. Therefore, the pixel shader has to deal with larger amounts of data, which implies that the pixel shader has higher expectations for performance. And as a consequence, pixel shaders typically run more slower than vertex shaders. However, applying, for example, lighting effects at the level of pixel shaders instead of vertex shaders gives you a higher detail. So performance is traded off for higher quality or details. Now, let's talk about HLSL programming language. What is it? It stands for High-Level Shading Language. It was created by NVIDIA and Microsoft. It is used for creating graphic programs for the graphics processor. It has a C-like syntax, also similar to HLSL, which is another related shading language. When we will be looking at the AST representations of HLSL code later, we will see exactly just how close the representation of the syntax in the AST is similar to C or C++. So, in HLSL, programs are written in a paradigm of implicit parallelism. HLSL is the supported language that direct 3D shaders are written in. It's currently the most popular real-time shading language in the world and is therefore the most familiar language to graphics programmers. There are multiple possibly different implementations, but there is no formal specification. So HLSL may not be 100% portable. And HLSL code is faster because the compiler is very aggressive, but sometimes too much optimized, so you can have precision errors. And on Intel cards, HLSL is better for compatibility, and older hardware is more likely to run without glitches. Here is a link to official Microsoft documentation about HLSL programming language. So what do I mean when I say that in HLSL programs are written in a paradigm of implicit parallelism? Before starting to write the code, we need to have an understanding of the paradigm used by such code. Writing code for parallelism in general involves two things. First, defining a subroutine which runs a single thread. Second, creating a mechanism allowing you to spawn and manage threads. In explicit parallelism, programming is from the outside perspective. Explicitly parallel code is when you have to manage multiple threads explicitly by yourself. Using pthreads API, for example, you decide how many threads to spawn, when they spawn, what data to give them, and questions of synchronization. What do I mean when I say that shaders are written with implicit parallelism paradigm? In implicit parallelism, programming is like the inside perspective. Implicitly parallel code looks like serial code. The code of a shader looks like serial code because the parallelism is managed by an external entity, which may be the API or the graphics hardware. The code of the shader is run once for every single pixel. Because the computation of each pixel is separate from the other ones, there is no data dependency. So all the computations can be run at the same time. It is an implicitly parallel code, which looks like serial code, because the input element is just the relevant data for one pixel. You do not need to have multiple threads for one pixel. Rather, each pixel is its own thread, and you are just writing a thread routine for that pixel. You are looking at the thread from inside that thread. Threading subroutines are always serial codes in relation to the piece of data input that they are given. Consider this example. Even in a threading subroutine, such as pthreads, it is serial code because only one thread is executing in that one function. We are not declaring multiple threads inside of it. It looks like serial code when looking from the inside, but when looking from the outside, it is a parallel code. In the pthreads code, the input is a particular element in the array. And in the shader code, the input is a particular pixel on the screen. And we can have different behaviors depending on identifying what is the exact input data element. But the code of the subroutine is serial when looking from the inside. It is serial in relation to itself. So I cannot really, just by looking at these two codes, I cannot tell the difference in the paradigm. They both look like serial code when looking from the inside. Well, that's because all the parallel code is actually on the outside, and when we're writing shaders, we don't have access to the outside because that is managed by the external environment. So when writing shaders, you're only creating this subroutine which runs over a single data input. You are not creating the mechanism to spawn and manage threads. That is automatically done for you by the DirectX environment. about HLSL programming language, data model, or paradigm. In shaders, there is no memory. All the data items are stored in virtual registers. There is no pointer support or interaction in HLSL. There is no heap segment and no dynamic memory allocation. No call stack either. Function calls are inlined in the place where they are called. Hence, recursion is forbidden. However, it's possible to fake recursion in HLSL by using 3 different methods. First is having nested calls to different functions, creating a new function body for each level of recursion. This only works if you know how many levels of recursion there will be in advance. And additionally, all the function calls will be inlined. So you have extreme duplication of code, which makes this approach impractical, useful for only small examples. Second is, since almost any recursive algorithm can in theory be written iteratively, eliminating recursion by restructuring the algorithm to fit iteration paradigm. Third is using an array in a virtual register to simulate a call stack of a fixed size, since you can't malallocate memory, together with an index that is used as a kind of a stack pointer. Now, let's talk about the control model or paradigm for HLSL. Shaders are supposed to be relatively small programs, instructions written in a sequential execution. Traditional uses for shaders, such as lighting, determining pixel color, and whatnot, have few or no conditional branches. Complex functionality should be in the C++ DirectX app, rather than in the GPU shader. Another thing is that GPUs do not have branch prediction. Every if statement makes the shader run slower, since the whole idea of a real-time shader is fast rendering speed. We sacrifice the convenience of that feature for speed. HLSL shaders have to run as fast as possible. I suppose that if you don't need that extra performance, you could add more features such as if statements to your code. But you can also avoid conditional branching by using conditional moves instead, such as the question mark colon operator is also an option for optimization. When programming HLSL, it is best to write a few short shaders that only do a specific task, such as calculating lighting, rather than one big uber shader that does everything. Stay away from God shaders, so-called, similar to God objects in object-oriented programming. Very large shaders are fine for offline rendering, where convenience is more important than speed. But for real-time shaders, we want to make the code as fast as possible, removing any bloated features that might slow down the code. So just keep that in mind. So HLSL programming language, it looks like a general purpose C-style programming language in the syntax, but in the semantics and the paradigm, there are these few things that you have to know. Now, there are 2 main compilers that are used for compiling HLSL code: Microsoft DXIL compiler and FXC compilers. So both compilers have the same command line interface. The FXC compiler is now deprecated. It is the old compiler. It is designed for handling very simple shaders, but not large complex ones with thousands lines of code, as might be sometimes seen in ray tracing shaders. So it has a long compilation time for such complex shaders. FXC compiler is supported up to shader module 5.1 only. This compiler is not based on LLVM. Optimization of generated code from HLSL source is limited, and as output it generates DXAssembly, a proprietary shader assembly code. Now, DXC compiler is the new compiler replacing the old one. Supports large complex shaders, such as ray tracing shaders, which may be thousands lines of code for certain special effects. We must use it if we want to use shader model 6 or above. It is based on LVM and it is an open source compiler. It can use the generic LLVM intermediate representation optimizations by calling libraries. As output, it generates DirectX intermediate language, which is a kind of LLVM intermediate representation with DirectX specific add-ons. DXIL is easier to use than DXIL for compiler developers because we can use LLVM C++ API for doing transformation and analysis passes on DXIL. We're going to cover that in a later presentation. DXIL is also more readable than DXIL because it is based on LLVM IR, which we have learned about in the previous several lessons. Both of these compilers also have their own C++ API for invoking the compiler programmatically. We want to compile HLSL code with these compilers, and both of these compilers have the same command line interface. So you can have use these options for DXC or FXC. So here are some couple common options. /T is the target profile. PS_5_0 means pixel shader with shader model 5.0. A shader profile is the target for compiling the shader. The first part of the keyword signifies the kind of shader used, such as a vertex shader, a pixel shader, geometry shader, etc. Second part of the word is the number of the shader model. The number of the shader model in the profile is the minimum hardware spec that will run our shader. Higher numbers of shader models have a lot more capabilities. Lower ones are really limited. Each shader model builds on the capabilities of the model before it, implementing more functionality with fewer restrictions. Next, /E is the entry point. Pixel is the name of the entry function, similar to main in C++. Then this option -big O small d disables all optimization, and -big O is specifying the optimization level as we are all familiar with. So this website, Shader Playground, it contains an easy way for experimenting with HLSL code and seeing what is the DXIL output code. So you first specify that you're using Microsoft DXC compiler. You then put a target profile in here, the entry point, and then you can check this option if you want to disable optimizations as well as providing the optimization level. And here you can put any arbitrary command line options that are not covered by the command line options above, which are these options right here. And then the output, select the DXIL. Then inside the output, furthermore, you can select to give you the disassembly, the DXIL, the LLVM IR code for that HLSL shader, or the Clang AST dump of the translation unit decal for that shader. Or simply you can print the compiler output to the terminal. It is the build output which is generated when you run this command, such as, for example, diagnosing bugs or error messages. Although we will be learning about HLSL itself, we will also study how it is represented in the AST and DXIL formats. It is good to know the high-level code, but knowing the internal representations of that code is just as important. And this is especially important because DXC compiler generates DirectX intermediate language code that is not completely equivalent to the HLSL code. Various optimizations can be performed. A clear connection between the original HLSL code and the resulting DXIL code is not always so intuitive. HLSL is only a high-level abstraction. However, the DXIL code actually matters at the end because it will be run on the GPU, or rather it will be passed through the Intel graphics compiler first, transformed in whatever ways, and then run. This slide, overview of HLSL file organization. Like C, C++ source code, HLSL source code files have a certain way of their organization. These are the different parts of an HLSL source code file that you can typically encounter, starting from the top of the file and going down. At the top of the file, usually you would see regular tweakables. These are elements of the FX framework, which is used by both FX Composer and 3ds Max for creating shaders. It is used to specify user interface elements. So GUI elements that the user can interact with and input data to the shader. So here is an example of a user interface element, which is a color picker for the user to manually pick the color of a pixel that they want for the shader. Next, we have the automatically tracked tweakables. These include matrices, which transform the coordinates from one space into another one. The shader uses these matrices to move data from one space to another. Here is an example. We are creating a matrix of 4x4 floats called WVP. And again, we will learn about all of these later. Don't worry. So after that, we have the shader structs. Two shader structs. Up to vertex is input from the application to the vertex shader. It contains the vertex data from the CPU. It is the input parameter to the vertex shader. And then we have the vertex to pixel. It is the output from the vertex shader to the pixel shader. So this should say vertex right here, vertex shader. It is the output to the pixel shader. It is the return type of the vertex shader, and it is the input parameter to the pixel shader. And after that, we can have several helper functions for self-contained code that the shaders can call, such as for achieving certain effects. And then we have the vertex shader and the pixel shaders as standalone functions, parts of the graphics pipeline. The vertex shader takes in up to vertex input from the application. It returns the vertex to pixel output to the pixel shader, and it transforms the vertex position to the homogeneous grid space. And the pixel shader takes in a vertex to pixel input from the vertex shader. It returns a float 4 color for that pixel, and it sets the pixel color to the incoming vertex color. So these are just two sample example vertex and pixel shaders. These are just very simple, but we will be looking at more complex examples later. here is the first shader example, the default HLSL code, which is displayed when you first open Shader Playground. It consists of an input struct with a color inside and an output, just a color. What would the corresponding DXIL code be? Since it is LLVM-IR, you would expect it to have a structure type definition, an object of structure type as input in the virtual register, and returning the input.color. However, the generated DXIL code is different. It returns void. We have no parameter to the main function, no structure type definition, no nothing. Instead, we have a bunch of function calls. What in the world? Well, it turns out that PS main here is actually not a real function. HLSL does not have real functions. From a high-level perspective, we think of shaders as functions that run on the GPU. However, you do not explicitly call a shader. Instead, they are automatically invoked by the graphics pipeline. The graphics pipeline decides what piece of data, what vertex or pixel that shader is to be called on and when. It is possible to write standalone helper functions that the main shader function can call, but those functions get inlined into the shader. They don't exist necessarily as real functions in the GPU. The DirectX API or the GPU hardware is responsible for passing the input from the previous stage of the graphics pipeline into the shader and for returning the output from the shader into the next stage of the graphics pipeline. The shaders are programmable parts of the graphics pipeline. Everything else is done for you. Think of an assembly line at the factory. These function calls right here are actually instructions to load the input from the previous stage of the graphics pipeline into the shader, which is equivalent to having an input parameter and storing the output from the shader into the next stage of the graphics pipeline, which is equivalent to returning a value from the function. That's why it is important to know both the high-level code as well as the low-level internal representation, because there may be a difference in how the programming language is executed on the machine versus how the high-level code is written. Input and output to the shader is such an example. So we take the red pill, so to speak, dive deep into the internal representation of the HLSL code, which is the AST and the DirectX intermediate language, and see how the code works in reality versus how we think it works. DXIL input output. So there are no function parameters or variables that correspond to signature elements, meaning input output structs. Instead, load input and store output functions are used to access the input output struct, element values and operations. The accesses are scalar, meaning not vectorized. Let's take a closer look at these two functions. This is the declaration of the store output function in the DXIL code generated by the compiler for the previous example. It returns void and it takes a whole bunch of parameters. These are the signatures of load input and store output functions from the official DXIL manual. So there are some important things to know. Load input, store output takes input output element ID. Input ID or output ID which is the unique ID of the signature element metadata record. Now, the row parameter is the array element row index from the start of the element. Similarly, the column parameter is relative column index. When generating code that assigns values into a float4 variable, the column parameter is like an index into an array of the float4. And the row parameter is also specified if the input or output is a matrix, meaning a two-dimensional array. And store output also takes the float value to store as the last parameter, whereas load input returns the loaded value. And you might be wondering, what is this no unwind attribute that's attached to these functions? So this function attribute indicates that the function never raises an exception. Raising an unhandled exception inside a function causes the function call stack to unwind. So that means if the function never unwinds, then it never throws an exception. If the function does raise an exception, its runtime behavior is undefined. I'm having 4 slides here left, so let's continue. Let's look at examples of variables in HLSL. So HLSL has the same primitive data types as in C, C++, plus some new ones, vectors and matrices. Vectors in HLSL are analogous to vectors in LLVM IR, meaning tightly packed variables. However, this is not the way that they are implemented. So here are different ways to initialize a float4 in HLSL. We can initialize it using just float4 and the different values. So this is the red channel, the color. This is the blue channel, the green channel, and the alpha channel, which is responsible for transparency effects. The different fields of float4 can either be specified all explicitly, or multiple fields can be assigned from another variable. So here we are declaring float2 with 0.2 and 0.9, and just a single float with 0.7. And then in float4, these first 2 fields are assigned from RG. Then this middle one is assigned from B variable, and then we are assigning 1.0. And then this is the DXIL output that is generated. So note that this row index is 0, 1, 2, 3. So this responds to the 0. Sorry, this is the columns index. 0, 1, 2, 3. So this responds to the 0th column, 1, 2, and 3. And because the variables RG and B are only used to be stored into the color and not accessed anywhere else, DXC compiler performs an optimization. It does not include those variables and the corresponding data copying instructions into the DXIL. It generates the code for the color only. And these hexadecimal numbers are actually bit representations of the floating point numbers in memory. This one is 0.2, this one is 0.9, this one is 0.7, this one is 1.0, which corresponds to these values in the color. Next example. This example demonstrates 2 points. First is any multiple fields of the float4 can be assigned into another variables. In this example, the middle 2 fields were assigned from the float GB, and this R is assigned here. And in the previous example, we have it the opposite way. The first two are assigned from the float 2, and then the middle one is assigned from the float. So these are just different ways that you can write it with the syntax. And second point is that float 2, float 3, and float 4 are required to be initialized using the function cast syntax. However, for float, you can initialize it either using the function cast syntax or using the C-style assignment syntax, as we saw in the previous example. This is the code. Once again, we are seeing the columns indexes increasing, and if you look at all the values that are stored there, it is 0.5, 0.2, 0.9, and 1.0. Example number 4. We are having this color A, which is the exact color that we saw in the previous example. It's the float 4, but now we are multiplying it by a variable bob. What is bob? It is a float value of 0.5. So whenever we are multiplying this vector of float 4 by the float, it actually does vectorized multiplication, meaning that it multiplies every one of these values by 0.5. And then it stores that into the resulting color. So each channel is multiplied by 0.5, which causes it to be half as bright. The final color is half as bright from the original one. And now we want to compile this into DXIL code and see what is being generated. Now, when compiling without optimization, DX compiler inserts a bunch of these weird instructions that don't do anything. At dx.nothing is a global variable initialized with i32.0. So these instructions are loading i32.0 value from that global variable. And the virtual registers are never used again in the code. These instructions seem to do a no-op, meaning no operation. Inclusion of these instructions does not make sense, since they were never present in the original version of the HLSL code to begin with. Maybe they are used for padding or alignment of the code segment. I don't know why they are there, but they disappear upon higher levels of optimization. And in my code examples, I'm compiling in level 1 of optimization to specifically omit these extraneous instructions. The other thing that we see here is that the float 2, and even float 4 do not make it into the final DXIL code. In the shader, the float 4 is returned. This is compiled into several store output function calls instead of just returning the instead of just returning the floating point constant values. The virtual registers are used here in the store output. So this is because the virtual registers are the results of fmod instructions. The vectorized multiplication of float 4 times the float is converted into 4 scalarized multiplications. So here we're multiplying each of these elements by 0.5. So multiplied by 0.5 right here, each of these values. And what's weird is that DXC compiler doesn't vectorize the code at higher optimization levels. That's not very nice. Anyway, this is the last slide, last example for today. Example 5, here we're having also the same code. The scalar A is being multiplied by something, but it is not a float now, it is a float 4. So when an aggregate of floats, such as float 4, is multiplied by an aggregate of floats of the same size, it does element-wise multiplication. Each element in the first aggregate times each element in the second aggregate, and it generates an aggregate with the same size, having the corresponding results of each individual operation. This behavior is the same in NumPy. If any of you are familiar, if you multiply two arrays together, it also does element-wise multiplication. Yeah, so here we are having these store output calls, storing the result of these fmol instructions. The first instruction multiplies the 0.5 by the 0.1. Then the second instruction multiplies by the 0.2 value by the 1.5 value. Then the third instruction multiplies the 0.9 value right here by the 0.5 value, and then the fourth instruction multiplies the 1.0 value by the 0.8 value. Conclusion, as in the previous example, it doesn't create all the intermediate variables. It just does the multiplication and then a store output. So when a vector type is multiplied by a scalar, the second argument is all the same. When a vector is multiplied by a vector type of the same size, the second argument in each multiplication corresponds to the elements in the second vector. And if the scalar is on the left side, then in the DXIL, the scalar would be on the left operand of the fmul instruction, and because the vector is on the right side of this multiplication operator, each element of the vector would be the right operand. So that is how multiplication of vectors works in DXIL. It is past 1 o'clock already, so stop here, but after that, for the next presentation, we will go over many more examples of taking code in the HLSL and compiling down into DXIL, and additionally looking at the AST representation to see how that code actually works.